we have our same tables as before, but now we have not only the evidence that the grass is wet, but also the sprinkler was on. Now let's see how the probabilities work out. We have the probability of R given W and S times the probability of W and S is the joint. We take the probability in W and S to the other side by calling its inverse sigma as before, and then we have the other expansion for the joint, which is the probability of W given R and S times the probability of S times the probability of R. Notice that the probability of R and S is inverted inside the sigma, and you also have a probability of S over here. In practice they'll cancel out, but for our purposes it's instructive to leave them as they are. The equation is perfectly valid as it is, and executing it in SQL simply by doing the join with the restriction that W and S are yes gives us select R sum of the products of all the P's from all the tables, where W is yes, S is yes, and now the only common variable is R, since S is yes is being restricted, and then we group by R. The result, since we're taking the case where S and R are both, or S and W are both yes, we get 0.9 times 0.3 times 0.2 as the only entry for R equal to yes. Nothing to sum up because the other pieces where S equal to no were left out, which is 0.054, and similarly 0.7 times 0.3, again 0.3 because S equal to yes, and 0.8. We get 0.168. Notice that we could have just as well omitted 0.3, but we left it there just so the SQL doesn't change. Normalizing so that the sum is 1, we get 0.05 by the sum, which is 0.24. That is, we have 24% chance now that it's raining, which is less than the earlier 42%. So what's happened is that our belief in whether or not it had rained first changes because we added a new possible cause, and then further changes when we observe that new possible cause to actually be true. So our belief gets revised because this belief propagates in the network, changing our belief about R once again. A final point, which is related to our hidden agenda again, is that the fact that we have multiple causes for a feature or an observation, and observing one changes our belief in the other possible cause, is an example of what we do every day. When we observe an event, we can explain away possible other causes, and in fact doctors do this all the time in diagnosing patients, and that's the example that we're going to study in our next programming assignment. Explaining away is something that is a feature of human reasoning and is also exhibited by Bayesian networks, and therefore the probabilistic reasoning is in some sense mirroring how we deal with uncertainty in the world. Do study Bayesian networks that we have done in this class using SQL. It's one of the easiest ways to understand what is happening in these networks. At the same time, it's not the most efficient way to do inference in Bayesian networks. There are many other more efficient algorithms. Having said that, it's also true that the linkages between SQL and inference in Bayesian networks has not been studied as much as it should have been probably. There are very few papers on this and probably no textbooks which talk about this way of explaining Bayesian networks, so you have to rely on the lecture notes alone for this topic. There are other algorithms for inferring or performing inference in Bayesian networks. The junction tree algorithm, for example, is very well known. In some sense, what that kind of algorithm does and what a SQL engine does inside to plan out the joins are very similar. in some sense, there's a deep relationship between how SQL optimization takes place and the junction tree algorithm. For those of you who want to explore further, this is probably an interesting area for some research. Anyway, now we shall turn to some other applications of Bayesian networks and graphical networks in general to learn about facts from text.